Hello anh em. Hôm nay thì mình sẽ chia sẻ cho anh em một cái khóa học mà mình đã từng làm cho bên Xtblock nè. Cái khóa này là lúc trước mà ngay cái thời đỉnh điểm GameFi á, thì cái kênh Xtblock có đặt hàng mình một cái khóa học về GameFi 101. Thì người ta đang bán ở trên kênh Xtblock với giá là 90 đô một khóa. Thì 90 đô thì mình được tầm đâu khoảng 20-30 đô gì đó. Thì mình đã bán được cỡ khoảng 6.000 khóa học rồi. Thì hôm nay mình quyết định mình sẽ không bán nữa mà mình sẽ lấy nó về mình chia sẻ miễn phí cho anh em. Cái hay của khóa học này là thứ nhất là nó rất là dễ nha, và nó phù hợp cho những anh em mà chưa biết gì, hoặc là cái gì cũng biết nhưng mà cái gì cũng biết sơ sơ, không biết là phải ứng dụng từ tất cả các cái thành phần đó, mình ứng dụng nó như thế nào để nó ra được một cái sản phẩm hoàn chỉnh. Thì đây là một cái khóa rất phù hợp. Cái thứ hai nó rất là ngắn, nguyên cái khóa học này nó tầm theo như mình nhớ là trên 2 tiếng thôi. Thì anh em nên tập nha. Mình sẽ chia sẻ một cái video 2 tiếng luôn. Bình thường ở trong khóa học thì mình cắt ra những cái video nhỏ nhỏ, rồi có câu hỏi, rồi có quiz này nọ. Nhưng mà hôm nay thì mình gáp được 2 tiếng. Anh em mà muốn học mà tự học trên YouTube á, thì hãy nên làm quen với thói quen đó. Anh em phải nhai được những cái video mà kỹ thuật nó tầm 1-2 tiếng kìa thì mới ăn thua. Chứ mà mấy cái video short mà tầm 2-3 phút hay là 5-7 phút thì không xi nhê đâu, không biết gì đâu. Rồi, nói vậy nha. Bây giờ anh em enjoy nhé.
Hello guys, I am Kelvin and welcome to Xtblock course on GameFi. A GameFi called Axie Infinity can have a valuation of $4 billion, and recently it got hacked with a value of $660 million. Yes, it is a lot of money. So how can GameFi become so popular? In this course, I'm going to show you how to build a GameFi step by step from start to finish. Also, I'm going to explain to you every aspect of GameFi. So let's get started. So let's get to the tools and languages that we're going to use for this course. For the gaming part, we're going to use HTML, CSS, and JavaScript. For database, we're going to use SQLite, which is a compact and lightweight version of SQL Server. For the APIs, we're going to use Node.js. For smart contract, we're going to use Solidity language and a framework called Hardhat. If you are familiar with these tools and languages, it is perfect. But if you're not, we're going to explain to you on the way. You can find the full source code of the course on GitHub repos of Xtblock. Let's have an overview of what we're going to do in this course. For the blockchain part, we're going to build an ERC20 standard token, which is going to be the utility token in the game. Then we're going to build a Vault smart contract which have the withdraw function and deposit function. The smart contract will allow the user to deposit their token into the vault and withdraw their token outside the vault. The vault then going to emit some events that's going to be listened by the bots. For the off-chain part, we're going to build a game which is a simple Flappy Bird game. Then we're going to build a database which store all the data of the player, how many balance they have, how many points in the game they have. Then we're going to build an API for the bots to call the API and update the database accordingly. So how's this going to work? The bots will listen to all the events that emitted by the blockchain components and then call the API to update the database accordingly. When we combine all these components, we'll come up with something that looks like this. So originally this Flappy Bird game do not have the blockchain functionalities. So I added the blockchain function. We can connect the wallet here. For connecting the wallet, we're using MetaMask and Wallet Connect. MetaMask is kind of the industrial standard that used to connect the wallet to all the dApp. Wallet Connect is a protocol which allows you to connect 300 of different kinds of wallets. So you open the application on your mobile phone, you scan the QR code, and then your wallet will be connected to this website. in this case, I'm gonna go simple with MetaMask. So I click the Connect Wallet button, I click MetaMask, and then I choose the account, I click Next, and then Connect. And yay, my wallet is already connected to the website. So in this wallet, I have a lot of FLP token here, and I have the amount of ticket here. The balance here is actually the balance of the FLP token, which is actually in my wallet. And I can convert from FLP token to in-game ticket and vice versa by clicking the convert button. So for example, I'm gonna deposit 100. I'm gonna deposit 100 FLP and I will get 100 ticket. I click convert. And then we wait for the confirmation. And when the transaction is completed, you can actually test it on Binance Testnet, because this game is running on Binance Smart Chain Testnet. You click on the transaction hash and you can see the transaction here. So the transaction says that I deposit 100 FLP, and if you got back to the game, and my ticket is added with 100 ticket. And we can do the other way around, which is convert the ticket to the FLP token. For example, I want 200 ticket and I want to get 200 FLP. I click the convert button and then we wait for the bot to process my transaction. And my transaction is completed. I can check it here, and as you can see, we have 200 FLP token. And if I get back to my wallet, and yay, I have 200 extra FLP token. So in order to play the game, I have to spend 5 tickets, and if I score 1 point, I will get 1 ticket. So let's try it out. So if I click play and I play the game, and I cannot score a point, and then I got deducted with 5 tickets. And you can see here the ticket we're gonna be deducted. Okay, so that is all about the products that we are going to build. Let's start building this. Hello guys, in this video I'm going to show you how to set up development environment for our project. So right here I have a folder called GameFi, which is a totally empty folder. So I'm going to open it with Visual Studio Code, and then I'm going to create another folder called Game, and then I create another folder called API, and another one which called Smart Contracts. Okay, and then in the terminal I will cd into the Smart Contract folder. Okay, so first of all we're going to make sure that we have Node, npm and yarn installed in our computer. So I type node-v. Yeah, we have it. I type npm-v. Yeah, we do have npm, and I type yarn.v. Okay, if you don't know how to install Node, npm and yarn, you can just Google it up. Awesome. So first of all, we're gonna init an npm empty project by typing npm init. Okay, and we do have the package.json file here, and then we're gonna install Hardhat package, and we're gonna use Hardhat platform to build all our smart contract. I'm gonna type npm install say dev Hardhat. You can grab a cup of coffee and come back in 2 or 3 minutes. Okay, so we have Hardhat installed. We're gonna init an Hardhat project by typing npx hardhat. And we're gonna use some TypeScript in this project, so I'm gonna create an advanced project that use TypeScript. Yeah, I know, but don't worry. That looks like a lot of files, but we just need to concentrate on some certain config file. So we're gonna look at the package.json file first. This file will store all the libraries and all the dependencies that you're gonna use in your project. To save time, I already created a list of all the dependencies with their versions, so that we can just paste it in here. So as you can see, we use Ethereum Waffle, EtherRest, Hardhat, and all the stuff here. To install all the dependency in the package.json file, I will type npm and install. You can grab another cup of coffee and wait for a couple of minutes. Okay, so we have all the dependencies we need right now. Another file that we need to edit is the hardhat.config.ts file, and as usual I already prepare a file for you, and we're gonna paste it here. So basically we will define some stuff in here. We will define the version of Solidity compiler, and we define different networks. This works great on productions because you can deploy your smart contract in multiple different networks with ease. So I define a dev network here, and we have BSC testnet, we have Solana, we have Polygon, we have mainnet, which stands for BSC mainnet, and we do have a object called the API key here, and we're going to use the API key to verify our smart contracts on the networks. Okay, and it looks like we're still missing the .env package here, so I'm going to just install it. I'm going to do npm install save dev .env. And the error is gone. Perfect. So let's try if this environment works. In the sample project of Hardhat, it's already provided with a sample smart contract called the greeter.sol. Also in the test folder, we already have the index.ts, which is the test script for greeter.sol. So I'm going to type npx hardhat compile to compile the smart contracts. Yeah, let's see. We are still missing something here, which called the env file. So we need the env file to store all our secret keys or our API key in that file. So I'm gonna create it right now. I'm gonna type in .env, and then I'm gonna provide the .env with all the information. Let's get back to the Hardhat config a little bit. So in here, we're gonna need a mnemonic phrase in the case that we want to deploy our smart contract on the test network. We're gonna need a private key of some wallet that they have pre-funded some BNB for gas, and we're gonna need a API key that is used to verify our smart contract on different networks. So we need to declare that in the .env file. So how can we get the API key? Well, in case of Binance Smart Chain, you just go to BSC scan and you follow the instructions. It is as simple as you register your Google account. For the private key, you go into your account, you click here, account details, export private key, and then you type in the MetaMask password, and here it is your private key right here. Okay, I think we're good. Then let's try to compile the smart contract again. And perfect, our smart contract is compiled. After the smart contract is compiled, as you can see, we can have a folder called artifacts right here. And if we go into greeter.json, we can find the API here. The API is the abstract interface that we're going to use to interact with this smart contract. Okay, let's try run with this test script. So I'm going to type npx hardhat test. And the test worked. Congratulations, you just set up your development environment successfully. Before ending this video, I'm going to show you some cool stuff that I used to do in my real projects, which is I'm going to write some script for our yarn deploy. So I'm going to write some script, compile, deploy, test, and verify, because these are the actions that we use a lot in development. So for example, you need to type npx hardhat test. When we already declare the script compile here, all we need to do is we type yarn test, and that's it. In the next videos, I'm going to show you how to create smart contracts with Solidity. Welcome back, guys. In this video, I'm going to show you how to create and deploy a token onto Binance Smart Chain testnet. First of all, we don't need this. I'm just delete all of these, and I'm going to rename it. I'm going to call it Floppy. And as usual, I already prepared the code so that I have time to explain it to you guys. So I'm going to use 3 templates from OpenZeppelin Solidity package, which is the ERC20.sol, the ownable.sol, and the ERC burnable.sol. So I just imported from OpenZeppelin, and then I create a contract called Floppy that is inherited from the 3 smart contracts that I imported here. Then we need to add the cap, which is the maximum supply that this token have. So in the constructor, I mint the cap to the msg.sender, then I transfer the ownership to msg.sender. One other thing I need to do is that I need to make sure that we do not mint over the total supply. So I have to override the mint function, and then I add in the required statement, which is the cap cannot exceed this number. And that's it. With 20 lines of code, you have a utility token. So let's try it out if this token is compilable. So I'm going to type yarn compile. Next, I'm going to show you how to deploy this smart contract on Binance Smart Chain testnet. First, I'm going to create a new file, and I'm going to call it config.json. And this is going to be the template of the config.json file, because in the progress of developing, we might need to deploy a smart contract over and over again. So it is a good practice to keep track of all the addresses of the smart contract on different networks. So I'm going to do dev network, Binance testnet, and mainnet, which stay for Binance Smart Chain. Then I'm going to into the script. So we have deploy.ts here. I'm going to add another file which call config.ts. So basically, this config.ts file is used to update the config.json file. We're going to use fs, which is stay for file stream, and we're going to update the config file accordingly. So we have the set config, we have the update config. Feel free to investigate the code. So in the deploy.ts, I'm going to write the deployment script here. So this part of code right here says that if we don't specify a network to deploy on, the default network will be on dev network. And then we're going to use the get factory function of Ether.js to get the factory, and from the factory we run floppy.deploy. Then we console log the newly deployment address, and then we update the config file. So let's deploy this smart contract onto Binance Smart Chain testnet. And yeah, it is deployed successfully. So you can see here we updated the config.json file. So on BSC testnet, the address of floppy gonna be this address. Let me show you this address real quick. So I can go to BSC scan, then I switch to BSC testnet, I input the address, and there you go, we already have this contract on Binance Smart Chain testnet. One more thing you need to do is that we need to verify the source code so that everyone come into here and they can read our source code. So to do that, I just need to type yarn verify BSC test and then the address of the token. And it is verified successfully. You can test it by click on the link here and it will lead you to the smart contract. So because it is already verified on Binance Smart Chain testnet, you can see the source code here, you can read all the public variable here, and then you can write the contract. In the next video, I'm going to walk you through some of the basic functions of the utility token. Let's have a look at the FLP token. Thanks to the config file, I know exactly what is the address of the floppy token on Binance testnet. I go to BSC scan testnet and then I paste the address here, and I can read the source code at the contract tab, so you can see the code of the whole smart contract here. In the read tab, you can read some of the information about this smart contract. You can have the total supply, you can have the symbol, the owner of the address, name, decimal, and etc. In the right tab, you can see all the functions that we can interact with the smart contract here. So there is a lot of function. There is transfer ownership, there is mint function, and on and on. If you are familiar with the token, then you should know what this function means. What I want to talk about in this video is the approve function, the transfer and transfer from function. These are the functions that help you to transfer funds from a wallet to another wallet or from a wallet to a smart contract. These are the concepts that usually confuse the new developers. Let's talk about the transfer function. If you want to transfer from an address to another address, you can simply call the transfer function and the funds will move from this address to this address. But what if you want to transfer funds from an address to a smart contract and a smart contract don't have the capability of dealing with that funds? So the funds going to be stuck in the smart contract forever. In that case, we prefer using the pool-based transfer, which is a 3-step transfer. The first step, you approve the smart contract to spend an amount of funds in your wallet. Then the smart contract will call the transfer from function to retrieve the amount, and the amount cannot exceed the max amount that you approve for the smart contract to spend. If everything works fine after the smart contract called the transfer from function, the amount that you approve will move from your wallet into the smart contract. That is exactly what the transfer from, the approve function, and the allowance state variable here. In the next video, we're going to use this pattern to retrieve user tokens. In this video, I'm going to show you how to create a Vault smart contract that allows the user to deposit the token into the Vault. I'm going to create a new smart contract called the Vault.sol. First of all, we're going to import the needed library. We're going to use 3 libraries. the save ERC20, ERC20, and then ownable. We're going to use the save ERC20 to have access to the save transfer from function. So according to the definition of the save ERC20.so, it says that it is a wrapper for ERC20 operations. Basically what it means is that it makes sure that all the transaction is reverted if there is any error in the process of transaction. And this is the interface for the ERC20, and this is the ownable, so that we can have the transfer ownership and renounce ownership abilities. I'm going to create a contract called the Vault contract. We need to define the token that this Vault smart contract is capable of receiving and sending. So I define a token here, and I use the ERC20 token, and then I create a function called set function so that we can always reset the token. Then we also need a constructor. So I created the deposit function that have one parameter, which is the amount. The required statement makes sure that the user have enough funds to send to this smart contract. Then I use save transfer from to send all the tokens of the user to this smart contract. Let's have a look at the save transfer from. If you look into the definition, the save transfer from function takes in 4 parameters, just like this, and then it performs a couple of checks to make sure that the transfer function will be reverted if there is something wrong. And that's it, we already have the deposit function. In this video, I'm going to show you how to create the withdraw function. First of all, we're going to import a library called the access control enumerable. The idea behind this library is that we only let the wallets that had the withdrawal roles to call the withdraw function. I'm going to extend this smart contract so that it is inherited from the access control enumerable. Then I'm going to declare a state variable called the max withdrawal amount, and then another state variable called the enable withdrawal, so that we can set the maximum amount per withdrawal, and we can set the enable or just disable the withdrawal functions. Then we're going to create the 2 set of functions to set those 2 variables. As you can see here, only the owner can set the withdrawal and set the max amount. Thanks to the ownable smart contract, we have the only owner modifier here. In the constructor, I will set the admin role to the owner of the smart contract or the msg.sender, which is the address that we use to deploy the smart contract. Now let's get to the withdrawal function. So the withdrawal function will have 2 parameters, the amount to withdraw and the address of the wallet that received the funds. You can see we have a modifier called only withdrawal here. We will get to that a little bit later. Then we got 2 required statements that only when the withdrawal enable state variable is true, we can withdraw, and the amount cannot exceed the maximum amount. After the 2 requirement is satisfied, if we pass the 2 required statement, I will call the transfer function of the token to transfer the amount to the address. Now let's declare the modifier only withdrawal. So in the modifier, I set the owner of the smart contract and the addresses that has the withdrawal role can call the withdraw function. Okay, so we are done with the withdraw function. Let's try compile this smart contract. And we have an error here because I forgot to declare the withdrawal role. I'm gonna do it right now. So this is just the way that the access control library works. This is how you declare a role. If you want to dig deep into this, you can also go to the definition of the access control smart contract, and you get the idea how they works. Okay, so let's try to recompile our smart contract. And it is working. In the next video, I'm going to show you how to write test cases for these two smart contracts. In this video, I'm going to show you how to create test cases for the Vault smart contract. I'm going to modify the sample test script a little bit. First of all, we're going to use a bunch of stuff that we need to import from here. So we are going to use contract, we are going to use signer with address, and we're going to use Jai at promise. Let me edit the describe block here. We're going to call it Vault. We're going to create our first test case, which is should deposit into the Vault. First of all, I'm going to create a helper function that helps us to parse in the number of ether easily. So every time you want to parse a ether, you need to call ether.js.util.parseEther. This is quite a pain. With this helper function, you just call parse ether and you input the amount of ether as a parameter. I'm going to declare the types of the variables that we are going to use. So we are going to define 4 addresses. Owner is the owner of the smart contract. Alice, Bob, and Carol are 3 addresses that we are going to use in the test cases. The Vault and the token are smart contracts. In the before each hooks, first I run the ethers.provider.send hardhat reset commands to the EVM to make sure that we have a fresh blockchain environment. Then I call the ether.js.getSigner to assign the addresses to the owner, Alice, Bob, and Carol. Then I deploy the smart contract, I deploy the Vault smart contract, then I deploy the token smart contract, and then we call the Vault.setToken and set the token of the Vault into the token address. Basically what this means is that every time it runs an it block, it will automatically run the before each hook block. Let's get into our first test case. First of all, we need to transfer an amount of token into Alice's address. Then we're going to call the approve function from Alice's address to approve the balance of Alice to the smart contract. Then Alice will call the approve function to approve her balance to the Vault smart contract. After the approval, Alice will call the deposit function. So let us expect after Alice calls the deposit function and deposit this number of token into the Vault, then the Vault will have the balance, which is this number. Okay, let's run the test case. And it is working. Next, we're going to write a happy path for the withdraw function. I'm gonna copy and paste the it block, and then I delete all of this stuff, and then this test case is called should withdraw. So first of all, what we need to do is we need to grant the withdrawal role for Bob. So I'm gonna put in here grant withdrawal role to Bob. And to do that, we should define a withdrawal role, and then we call the grant role function and grant the withdrawal role to Bob address. So we have an error here because we have not imported the Kitcheck library. I'm going to do it right now. I come up here and import the Kitcheck library from ethers.util. Okay, and the error is gone. Next, we need to call the setup function to enable the withdrawal function of the vote. To do that, I'm going to call the set withdraw enable to true, and then I'm going to set the maximum amount of token is 1 million token. Next, we need to deposit into the vault so that the vault can have some balance in there. So I transfer the token to Alice, and then Alice call the approve function and then the deposit function. Then Bob, as a withdrawer, can call the withdraw function and withdraw the amount of token into Alice's address. So after Bob called the withdraw function, the balance of the vote should be deducted and the balance of Alice should be added. So we expect the balance of vote should be this number and the balance of Alice should be this number. Let's run the test once again. And we got 2 passing. In the next video, I'm going to show you how to create test cases for the unhappy path. Welcome back, guys. In this video, I'm going to show you how to write unhappy path test cases for the Vault smart contract. I'm going to put a comment up here, which is the happy path, and then down here we're going to go for unhappy path. Okay, so the first unhappy path is for the deposit function. If someone tries to deposit more than they have, then the transaction should be reverted. So I'm going to copy and paste this case it blocks here. The description should not deposit, and the return error should be in the Vault smart contract, and it should be reverted with this message. So I'm gonna copy it and then I put it here. Okay, so just the same as the happy path, when Alice tries to deposit more than she can have, then we should expect this line to be reverted. So Alice have 1 million ether here, but if she tries to deposit, for example, she wants to deposit 2 million, we expect this whole statement will be reverted. So I will put expect here, and then this whole statement should be reverted with, and then we put the error message here. Okay, let's run the test. And it is working. Next, we're going to create the test cases for this required statement, which is when the withdrawal enable is false, then the withdrawer cannot withdraw and the transaction will be reverted with this error message. Okay, so I'm going to copy the it blocks here. I'm going to copy it down here, and then this one we call it should not withdraw, and the error message should be this message. So first of all, we're going to grant the withdrawal role, then we set the set enable withdraw, we set it to false, and then the maximum amount, yes, we set it to 1 million ether. Alice deposit to the vault, then Bob withdraw to Alice, but this time we expect that the statement will be reverted. So I will expect the statement to be reverted. Expect, and the error message should be this one. Let's run the test, and it is working. Next, we're going to do the same for this required statement. So I come back to the index, and I just copy and paste the whole story here. This time I set enable withdraw to true, and then I set the maximum withdrawal amount to this number, which is 1000 Ether, and then Alice deposit into this. This is fine. And then when Bob try to withdraw more than 1000 Ether, it should be reverted. 2000 Ether, and it should be reverted with this error message. So expect the vote to be reverted with the error message. And everything works fine. Now we're going to create the test case for the modifier here to make sure that only the owner or the withdrawal can call the withdrawal function. I come back to the test cases and I copy and paste the story, and then the error message should be caller is not a withdrawer. And then we set the withdraw enable to true, and the maximum amount is 1000 Ether. Okay, and then I'll just deposit into this, and then this time we're not exceeding the amount. We just put in here 1000 Ether, but this time it is not Bob to call the withdrawal function, but Carol is the one to call the function. Carol is not a withdrawer, so it should be reverted. We run the test. And it works fine. It looks like we performed the test on every required statement and modifier of the smart contract. But let's look into the situation where the withdrawer tried to withdraw more than the balance of the vote. As you can see in the withdraw function, we don't perform a test of the balance of the vote. So let's try it out to see what happened. Back to the test. And then I copy and paste it here. And this one we get the error message blank, and then we try to set enable to true, and then we set the maximum amount to 5000 Ether, and then Alice deposit into this 2 Ether, but Bob, the actual withdrawer, is trying to withdraw 3 Ether. In this case, the balance of the vote will be 2000 token, but the withdrawer is trying to withdraw 3000 token. So let's see what happened. So as you can see, the error message here, ERC20 transfer amount exceed balance. But in the vote smart contract, we don't perform this test case. So why is that? If you look into here, the library that we use, so if you go to the definition and then you search for the transfer function, and the transfer function will call the dash transfer function, and if we go to this one, and you can see the error message is here. Thanks to the community vested code, it is already right written, and we can safely use those library. So I can just put the error message here, and then I put that in my test cases. Then I put that in index.js, and this one should not withdraw with the error message ERC20, and I expect it to be reverted. And we run the test again, and it is working. So I just performed some basic testing here to get you the idea. You can come up with whatever amount of test cases that you want. I'm gonna stop the video here. In the next video, I'm gonna show you how to deploy the Vault smart contract to Binance Smart Chain testnet. In this video, I'm going to show you how to deploy 2 smart contracts on Binance Smart Chain testnet. So this is the deployment script that I did for the floppy.sol. I just copy and paste the whole script, and then I rename this to be Vault, and this one gonna be Vault, this one gonna be Vault with a lowercase, and then with this the uppercase. Then we console log the address, we set config, this is going to be the Vault, and this is going to be vault.address, and then we update the config file. Let's run this deployment script. Okay, so it is deployed successfully on Binance Smart Chain testnet. Let's get back to the config file. So in the config file, we have the smart contract addresses here. So the Vault smart contract will be this one, and the floppy token will be this one. Let's verify the 2 smart contract source code. I'm gonna verify this one first, and it is verified successfully. Let's control click to the link, and we can see the source code here. Let's get back, and then we continue to verify the other one, which is the Vault smart contract. I'll copy the address here and I put it here. And the Vault is verified successfully. Let us click here, and we can see, yes, it is the Vault source code right here. And congratulations, if you follow me this far, we have done with the smart contract part. In the next section of this course, I'm going to show you how to interact with these 2 smart contracts. Welcome back, guys. In this section, I'm going to show you how to create a database and an API to read and write to the database. So we will come into the API folder, and I will create a folder structure so that we get everything organized. I'm going to create a new folder called contracts. So we will store all the API of contracts into this folder. Then another folder called controllers, then another one called data, and then another folder called routes. In the scope of this smart contract, we just interact with 1 smart contract. We just have 1 controller and 1 route, but it is a good practice to follow the folder structure so that when the project got bigger, you get everything organized. Okay, get back to the API. I'm going to open it with Visual Studio Code. And I'm going to create a new file called server.js. This is going to be the entry point. So when you run the API, you just run the server.js file. First thing I want to do is I want to init an npm project by typing npm init. So we init a npm project. So we got the package.json file here. I'm gonna add the dependencies for this project. So for this project, we're gonna use the .env, the SQLite 3 for database, and Web3 to interact with smart contracts. To install the dependency, I type npm install. You can grab a cup of tea and get back in a couple of minutes. And yes, that is how we set up the environment for the API. In this video, I'm going to show you how to create a database with 3 tables: the player match table to store all the information of the player who playing the game, the table player vault who store the balances of the player, and the vault transaction table to store all the transactions with the player who interact with the smart contract. As you can see here, I'm using SQLite Studio to read the SQLite file. I will put the link to download this tool in the description of this video. Now I will get into the data folder and create a new file called migration context.js. I'm going to run this script to create the table. First, we're going to import SQLite. We're going to use this package to create the tables. So I will put a command here: create a new raw database. So I will write a function to create a new database. So this function here, I create the database called fluffybird.db, and the location will be outside of the data folder, which is in the API folder. So if it is created successfully, I will console log data created successfully. If there's an error, then we'll log the error. After creating the raw database, we're going to run the database init function to create the table. I have not defined the function database init, so I'm going to do it right now. So I will put the command right here: init the tables for the new database. So it is purely SQL statement here. I create the table and then I create the column name, the data type, etc. So we're going to run create raw db at the bottom. And you can see here we have a database called fluffybird.db. In the next video, I'm going to show you how to read and write the data from the database. Hello guys, in this video I'm going to show you how to create a class that we're going to use to store all the SQL commands that we use to select, insert or update into the database that we just created. So in the data folder, I'm going to create a new file and I'm going to call it cstorecommand.js, and I'm going to create a class called cstorecommand, and I'm going to export the class. In the cstorecommand class, I'm going to create a constructor. And in this constructor, we will define every SQL statement that we're going to use. So the first one I want to do is I want to add new player and set the initial points to 10. So I'm gonna define this statement. As you can see here, this is just pure and very basic SQL statement that I'm gonna use. We do it this way so that when we try to call the statement, we don't have to input the whole statement, but we just need to call the add player vault command from the class. Okay, and the next I'm going to do is I want to get for active player, and then I will define the SQL command for this one. The next SQL statement is that I want to get the top players by their points. So this is very useful when you do something like the leaderboard and we will get the player by their points. So I will define the SQL statement for this one also. And then the next one is add ticket to a player. We're going to use this command to add the ticket to a player when they play and they win some ticket or they deposit the FLP token into the game. So I'm going to define this as well. And it is the same for deduct player ticket. Next, we're gonna go for insert new match info. When the player starts a match, and this is the SQL statement for this one. And the next one we want to do is we want to update the end time of the table when the player finishes a match. So we're going to go for update the end time when the player finish a match. And we're going to define this. Next thing we want to do is we want to insert a new record to the vault transaction so that whenever there's a transaction into the vault, we're going to create a record. And last but not least, we want to update the transaction hash into the vault transactions so that when the transaction completed, we have the transaction hash. And we are done with the CStore command class. In the next video, I'm going to show you how to create a data adapter object so that we can handle the connection to the database and use the SQL statement to interact with the database. In this video, I'm going to show you how to interact with a smart contract through an API. In the scope of this project, the API will interact with the FLP smart contract to retrieve the balance of a specific address. It will also interact with the Vault smart contract and call the withdraw function to withdraw funds from the Vault to a specific address. In order to interact with a smart contract, you're going to need the API and the address of the smart contract. I will put the address of the smart contract in the .env file. So I come back to the smart contract project, I go into the artifacts, contracts, floppy.sol, and I have the floppy.json, and I grab the API here. So I'm gonna grab it here, and I come back to API and contracts, and I create a new file, and I'll call it floppy.json, and then I paste the API here. For the address, I'm going to go back to the smart contract, and then I go to the config file and I grab the floppy address right here. And I put it in the env file. So we have the address here and we have the API, everything's ready. Now we're going to create the script. So I'm going back to data, and then I create a new file called smart contract data object adapter object.js. We're going to import .env to read from the env file, and of course we're going to import web3, and we're going to import the floppy API right here. Then I'm going to create a new class called the smart contract data adapter object. Then I'm going to create a constructor, and we'll define the network and the token address in the constructor. So this function is retrieve the balance, the FLP balance of an address. As you can see here, first I create a contract object and I input the API and the address, and then I call the balance of function of the FLP smart contract. I input the address as a parameter, then I do some data manipulation, and then I return the value. If there's an error, we return null. And that is it. That is how we can retrieve FLP balance of an address. In this video, I'm going to show you how to call the withdrawal function of the Vault smart contract. Let us recap the logic of this function real quick. In order to call the withdrawal function, we need to call it from a withdrawal role address. So we need to assign a withdrawer to the smart contract. So I will open the config file real quick, config.json, and then I copy the address of the vault. I go to BSC scan testnet, copy the address here. I go to contract and read contract. So we're going to need to connect the owner address of this smart contract in order to set the withdrawal address. So the owner of this contract is this address, and the byte 32 of the withdrawal role going to be this one. So I go to the write contract tab and I connect it with the owner. I will call the grant role function to grant withdrawal role to an address. So first of all, we need to grab the byte 32 of the role and put it into here, and then I will choose an address to grant the withdrawal role. Copy the address and I input it here, click to write, I click confirm, and I can view the transaction here, and I can double check if the address is already a withdrawer by input index 0 and with the withdrawal here. And yes, it is already a withdrawal. So then I will get back to the code. We're going to update the env token because we're going to input the withdrawal private key here so that it is really secure. So the vault address, withdrawal address, and we paste it here. And for the private key, I'm going to export the private key. I paste the private key here, and it is done. We already done with the env file. get back to the smart contract DAO, and we are ready to interact with this function. So I'm going to define the address in the constructor. We grab that in the .env file. First of all, we're going to add the private key so that we can sign the transaction with the withdraw private key. This is just basic contract interaction where we initialize a contract object and then we call the withdraw function, send from the withdraw address, we specify the gas fee, and then we handle and return the result. And that is it. That is how we call the withdraw function from the vault address. In this video, I'm going to show you how to create the API controller, which is the most important part of the API. So in the controller, I create a new file. I call it API controllers.js. And then I'm going to import the files that we're going to use. So we're going to use the Fluffy Bird data adapter here. We use the smart contract data adapter. The match code is 5, which means that every time a player play a match, we will deduct 5 points from them. And I define the path to the database here. So basically what we're going to do is we initialize a object from the data adapter, and then we call the functions in that object. So I'm going to go for the basic functions first. As you can see, if we want to get the balance, we just initialize a new object of the smart contract data adapter, and then we return the result of the get balance function. This is the same for add player, the same for get top player, and add ticket balance, withdraw ticket balance, and update transaction hash. Next, we're going to create a function to get the ticket balance of a player. This is going to be a two-step function. First of all, we're going to add the player if the player is not exist, and then we're going to get the player balance. So I will put the comments here. If the player is not exist, then create new player. So I will call the add player vault to create a new player. If the player already exists, then the add player vault will return an error and this will not run. So we just run the get player balance and we pass in the address, then we handle the result. Next, we're going to write a function to start a player match. So this function is also a two-step function. First of all, we will deduct the point from the player, and then we will call the start player match. So I will put a comment here. Deduct the ticket first, then start the match. Next, we're going to build the end match function, which is also a two-step. First of all, we will call the end player match to end the match, and then we will add player balance, which is we will add the points to the ticket. So I will put a command here, end the match, and add the ticket. Next, we're going to export all the functions so other components of the API can call the functions. So I'm going to put here, we're going to export the functions. So as you can see here in the export function, first of all, we're going to grab the parameter from the request body, and then we will return the result with status code. Status code 200 usually stands for success. We export the start match, and then we export the end match, and we export other functions. Get balance, get ticket balance. Next, we're going to export the withdraw function. So we need to perform some data manipulation here. First, we grab the address and the amount from the request body, and then we will deduct the point, and then we will call the smart contract, which is the smart contract DAO, to send the token to the user. So it's gonna be a 3-step function. And last but not least, we're gonna export the deposit function. The front end will call this function after the user deposit to the vault, and this function will add the ticket to a player. First of all, we grab the parameter from the request body, and then we add ticket to the player, and then we return the result with status code. In the next video, we're going to create the route which routes the request to the specific endpoints, and then we will put everything into the server.js and we start the server so that the API is up and running. In this video, I'm going to show you how to create an API route, also how to set up an API server using the Express framework. First of all, I come into routes and then I create a new file called API routes.js. This component will route the request to the corresponding API endpoints. So in this file, we define the type of the request, get or post, and then we route it to specific endpoints. And of course, we use the API controller that we defined earlier. That is all for the routes. And now I'm going to show you how to create the server.js. We're going to create the server.js using the Express framework. Express framework is a very popular framework to create web applications and web APIs. You can grab this code template on the Express documentation output in the link below. So we're gonna initiate a Express instance here, and then we do a couple of config. For example, you can set the port here, the port that the API will run on, and then we can set the timeout of one request, and then you set the request status. Next, I'm gonna import the routes that we defined earlier. Then we will register the route by calling the routes and put the app as the parameter. Then we're going to call app.listen on specific port, and then we console log so that we know that the API is listened on a specific port. To start the server, we run node server.js. Welcome back, guys. As you can see from the previous video, when we run the server.js, it returns an error. In this video, I'm going to show you how to debug this error. Actually, reading the error messages and debugging your code is a really good way to learn. First of all, I'm going to add a helper.js file, and I will export the function API return to handle the errors in the API code. And in the API controller, some of the functions we use API return here, but I forgot to define it in helper.js. Also, I added the vault.json in the contracts folder. This is the ABI for the Vault smart contract. We add it here, and then we define the Vault API object so that we can use it in the smart contract data adapter. And for other components to use the smart contract data adapter, we need to export it. So I added the module.export smart contract data adapter. And that is it for the debugging. Now you can run node server.js. And the server is started on port 3000. Next, I'm going to show you how to test the API. We are going to use a tool called Postman. Postman is a very powerful tool that lets you create API requests and handle the API responses. So I'm going to use this to test all the API endpoints that we built earlier. And hopefully we don't have to do any debugging for now. I created some request template in the API route so that you can see the result of the API request. So we get back to here. First of all, we're going to test this API, which is get ticket balance. This will return the ticket balance of a user in the database. So I copy this, and the method gonna be get. I paste it here, and I click send. And the balance is 1505 and message is success. And from the console logs, you can also see the result here. Next, we're going to test the get balance. This will return the balance of a wallet in FLP token. So I'm going to copy this. This is going to be a get request. So I paste it here and I send the request. And the balance is 50. And message success, so the API up and running. Next, we're going to call the start match endpoint. The start match endpoint will deduct the ticket of a player and start the match. So I already prepared the script here. We paste it in here and we send the request. And the message is success, and it returned the ID of the match. So if we scroll down, we can see the ID of the match right here. The next endpoint is the end match endpoint, and it is a post API. So we come back here and we choose the method is post, and then we modify the endpoint, which is the API / end match, and then we need to modify the body of the request, and it's gonna be in raw JSON format, and it's gonna be like this. In this case, the body will contain the address, the ID of the match, the point of the match. In this case, the match that we just started is ID 2, so I put ID 2 in here, the point that the player earned in the match. And this one is an extra field that we leave here if we want to track more information about the match. I click send, and it will return the total points of a player. And we need to double check in the SQLite Studio. If I go to the player match and then I go to data and I refresh this, and as you can see here, the match ID number 2, the player earned 100 points. So we can update the database by calling this API. Next one, I'm gonna call the get top API. This is a get request. So it is quite easy. We just create a new one and I paste it here, and it will return the top players. Next, we're going to test the deposit API. We're going to call this API when a player deposits into the vault, and when the transaction is completed, we need to add the points in the database. So I'm going to get back to this method post. I input the base URL here /API/deposit, and then in the body we will contain the body. So we're going to input the body. In this case, this wallet had deposited 200 FLP into the game, so we need to add 200 points to their profile with the transaction ID. So I send this, and the message success, and this wallet now have the balance of 1800 tickets. And now for the last one is the withdrawal. We're going to call this API when a user want to withdraw their ticket into FLP token. So I'm going to test this. I'll copy the base URL. And then the body of the request. The withdrawal will call the withdraw function in the Vault smart contract and withdraw 50 FLP into this address. This time we're gonna have to wait a little bit longer because we have to call the smart contract. So already connected to the database to update the balance of the player. Then we're gonna call the smart contract to transfer the token into their wallet. And the request is success, and you can see the transaction hash here. We can actually scan the transaction hash on testnet. So I go to BSC scan testnet, and I search for the transaction hash, and you can see the withdraw 50 FLP token. And that is it. Congratulations, every API endpoint is working. In the next section, I'm gonna show you how to create the game, and then we will combine every component together to come up with the final product. So stay tuned. Welcome guys, in this section I'm going to show you how to turn a normal game into a game file. I found this repository very interesting. It is Flappy Bird of Naizbest. Flappy Bird is a very classic game that already been proven really interesting, and it can earn millions of dollars back in the day. So I go to this link and I go to code and I copy the link. Then I come back to my project, right click here and I create a new Git here, and I just clone the repository. And it is done. I'm gonna call it game, so I'm gonna rename it, or I just leave Flappy Bird just like that. So I right click and open with Visual Code, and as you can see here, it is really simple with HTML, CSS and JavaScript. All the assets, all the sounds and images is stored in the asset folder, CSS file here, and all the script is stored in the GS folder. And then we got the index.html, which is the HTML code that the client will run. So we right click here, open with live server, and congratulations, we already have a Flappy Bird game running on our local computer. Hello guys, in this video I'm going to show you how to add blockchain component into the game. So basically we're going to handle the connect wallet button, and when we click here it's going to pop up the MetaMask or wallet connect connection. And if we try to connect with MetaMask, there's going to be a little bar right here to display the address, the BNB balance, FLB balance and ticket balance. Also when we click the convert button, it will show the convert ticket dialog that helps you to convert ticket to FLP or vice versa. If you go this far, then I believe that you already have some knowledge on HTML and CSS.
Yeah.
And that is it. Congratulations, we already have all the component and the styling for them. Hello guys, in this video I'm going to show you how to interact with an API using the Axios library. First of all, we're going to add a new JS file, which is the jQuery UI. jQuery UI.min.js. This is the library that contains all the transition effects that makes your website look a little bit sexier. So I'm going to copy and paste it here. I will put the link to download all the script in the description of this video. And then I will create a new folder, and I'm going to call it Web3. In Web3, I create a new file called api.js. First, I will create an Axios instance. Then we will create the base URL because I already deployed the API to this address. But if you want to run it locally, you can change it to localhost and port 3000. Then we're going to create a helper function that's going to return the data of the result. We just want to grab the data from the result, so if the status is different than 200, then we return an error. And if the status is 200, we will grab the data from the API response. Next, we're going to create a function to get the ticket balance of an address. The structure of the functions will be similar. We just input the correct parameter and we call the correct endpoint, and we will get the result. Next, we're going to create the deposit API. Then we will call the withdraw. And then the start match API. And lastly, the end match API. And then we come back to index.html and we look for the script part. Because we are using Axios, so we need to reference the Axios library. And then we will reference the api.js in the index.html. And that is it. That is done for the API call. Hello guys, in this video I'm going to show you how to call smart contract and implementing game logic into one file. First of all, we're going to need a library file. So I'm going to open this in Web3. So we're going to need Web3 provider, web3.min.js, and web3.model.index. If we install Web3 as a package, we automatically have this file in the package. But we decided to go simple with HTML, CSS, and JavaScript, so we need to copy the file manually. I create a new file called web3.js. So in this file, we're going to use the Wallet Connect provider. Wallet Connect is a protocol that helps you to do the wallet connection with more than 300 kinds of wallet. I'm going to define the FLP address and API, also the Vault address and API. As you know, in order to interact with a smart contract, we need the address and API, so I defined it here. Also, I define a couple of parameters to input into the transaction call. Then we create some variable to manage the account and the account information. And we define an init function. In this init function, we define the network, which is the Binance Smart Chain and Binance Smart Chain mainnet. And we initialize Web3 model with a bunch of parameters. And then we're going to create a helper function for short address. So this is going to be the helper function for address. So in many cases, we don't want to show all the address on the UI, so we need this function so that the address is going to look like this. Next, I'm going to create a function that will fetch all the needed data of an provided account. So this is going to be fetch data. So we will fetch all the data in this function. We get the chain ID, we get the accounts, then we call the web3.if.getBalance to get the BNB balance of this account. Balance of is from the API.js to get the ticket accounts of that address. Then we call this function to get the balance in FLP. Then we define the HTML tag code to help display all the data that we can fetch. Also, I'm going to create a function to refresh the data, and this one we'll call the fetch account data. Then we will create the deposit function. So first, we will call the approve function of the Floppy smart contract, and then we will call the deposit function of the Vault smart contract to move the funds from the account to the Vault smart contract. Then we will call the deposit API to add the ticket to the player. Then we will define a function to get FLP balance. So to get the token balance, we interact with the smart contract and call the balance of method. Then we create a function that will handle a couple of events. So this is going to be functions to So we will call the onConnect function when we click on the Connect wallet, which is right here. And this is the same when we click the disconnect button. And this function onShowConvertModel is to handle the action when you click the convert button and the dialog pop up right here. And the function onConvertTicket is to handle the action when we click the convert button. And the onConvert function is to handle the action when you click this arrow, and you can see is revert from FBIRD to ticket and vice versa. And finally, we will add the event listeners. And that is it. We are able to interact with the smart contract and call the withdraw and deposit API from the API.js to implement game logic. Welcome back, guys. In this video, we're gonna finalize the index.html and the main.js file. This is going to be the last video of the coding process, so congratulations for going this far. First of all, we get to the index.html file and we reference to the script that we just added, which is the free library of Web3. And then we're going to reference the Web3 model.js. So pay attention here because I put the Web3 model.js under the API.js so that the Web3 model can call the function from the API.js. If we do it the other way around, which is put the Web3 model.js on the top, then it cannot call the functions of the API.js. So the sequence of the references have to be like this. And then we get back to the main.js file. So there's two things we need to do. When we start the game, we need to call the start match API. And when the player is dead, we need to call the end match API. So I search for the start match function. It is the start game function at this line. And because we have the await keyword here, so the start game have to be an async function. And that is it for the start game. And then we need to find a function called player dead to call the nmatch API. So I check dead, and you can see the function player dead here. I go to the definition, and that is it. And I'm gonna call the nmatch API. And because we have the await keyword here, so we need to put async function here. And that is it. We are done for the coding of this product. So because I already deployed it to the internet, so you can go to this URL and experiment the game yourself. You can always download the source code on EtherBlocks repo. In this course, we cover a lot of topics. We talk about smart contract development, testing and deployment. We talk about APIs and database. We talk about smart contract interaction, API calls, front-end, HTML, CSS, JavaScript, and that is a lot of topic. But have you ever wondered what else we need to do if we want to roll out a product? In this video, I'm going to give you a sneak peek of what a real GameFi product looks like. In the real world, we will ask the user to sign with their signature, and then we will grab that signature, assign them an authentication token, and they will use that token to interact with our APIs. That is to make sure that only the owner of the wallet have the privilege to call the APIs that is associated to them. Talking about API securities, there's a lot of security issues that we're going to have to deal with. In the API, we will restrict the IPs that have the privilege to call our API. Also, we will restrict the domain names. We can even go further with the firewall rules working as a gateway, so the firewall will block every request that comes from untrusted source. With contract interaction, we will put all the requests to a contract into a queue. You can use queue from third party like Google or just code it manually. I personally like to code it manually because it is more convenient. Then we will create a separate process that checks all the objects in the queue to prevent DDoS attack to our smart contract. Talking about API call logic, we don't call the API directly. As you can see in this course, after we interact with the smart contract, we interact with the database through the API directly in the same functions. But in the real world, the smart contract will emit an event, and then we will have a separate process to listen to the event and call the appropriate API endpoint. And for the database, in this course we use SQLite, and it is a free version of SQL database. But in the real world, we will use enterprise level database such as Microsoft SQL Server, AWS Snowflake, or Postgres. Then in the database, we will create roles and assign certain users into certain roles. Within this course, we use select statement directly, but in the real world, we will use store procedures, and only certain users with certain role can call the appropriate store procedures. We implement a mechanism called the table lock, so that whenever a process is writing to a table, that table is locked. That is to prevent the race condition attack. And that is just some little sneak peek about the security issues. With big projects, we will have third-party auditors and security experts. Even some projects have invited 2, even 3 third-party security experts to become their partner and work on all the security issues. That is it. I hope you enjoyed this course and thank you for going this far.